Some of the ones that we've been in Portugal already know. So indicators are just, how can I say, it's a way of simplifying the information. Imagine that you have a river and that you have every minute a measure of temperature, okay? And then you have thousands of data. And you look at the data, and can you say if the trend is increasing or decreasing? It's very difficult if you have, you know, every minute measurement. So it's really difficult to get those trends. So when we speak about indicators or indexes or whatever, we are just speaking about looking at some parts of the data that can indicate us where are the trends going to. For example, we can look at minimum temperatures every day. What is a minimum temperature every day or every year or every month? And then we will have a much simpler graph, okay? Or we might look to variability during the day or during the months or during the year. And that's another type of indicator. So the idea is that we simplify the information from thousands of data we receive. And we use this for decision making, communication to the society, for understanding what is there. So it depends really on what we are looking for. If we are looking to climate change, pollution, whatever, it's important. And sometimes it's not the averages that we are looking for. We are looking to the maximums, to the minimum, or to the variability of the system, because those normally are the signs what things are going, you know, better. It's like in medicine. If you are going to the doctor and you see some indicators, for example, you look to some measurements in your blood which are not directly related to the disease, but which are an indicator of something is wrong. Then you need to do an extra analysis to check that, okay? So those are the surrogates that we are looking for. So we are looking for, like, temperature in the ecosystem. We are looking to signs that things are not going well, and we need to first do that because we might need to understand better what is there. So we need to go deeper in the knowledge, or because we just need to communicate information. And then we, okay, if you are pregnant and you have a contraction when you are having the baby, you have all this monitor that helps doctors understanding if you are almost delivering the baby or not. So this is just a way to do it. It's the same thing as in health, okay? So we need to go for this thing going to indicators. So as we go to the indicators, we have these, we are aggregating information, and we have lots of information, we have a lot of data, so we are losing data, but then we get perception of things going on. So it's a way of, we lose data when you come here. So for example, if you just go to the minimum temperature and then the question changes, we need to go back again and look at the other data, okay? So we cannot always use the same indicator for everything. It depends really on the question, okay? So this is used for lots of things. For health, for economics. So GDP, for example, it's the example of an indicator. Or, for example, human society also use this for example, the number of, I don't know the name in English, but when the number of babies well, I don't know how the name in English to say that, but sorry, mortality at birth rate, at birth date versus mortality at birth. So, for example, mortality at birth is an indicator of the society, or education, at what level you get education. So this is the kind of an example you can use as an indicator. So it doesn't tell you how many babies you have in that country. It doesn't tell you how many, you know, it just tells you a small number. And for example, we can have like about 3 as in 1,000, 3 babies. So the rate of mortality is normally it's a number within 1,000 children born. And for example, 3, it's a number of which is a very good number. For example, if it's 10, it's a bad number. And we know just that, and we use that information to see how society is sustainable, it's economical good, or wherever. So this is the kind of thing normally we use. Okay? So this is just what I've been telling you, it's just for you to stay with information. So it's looking at the environmental indicators, and now going to the environmental indicators. They started after the 70s, when there was this petrol crisis, and then people understood that the natural resources were limited, that we could not use more natural resources because population was growing so fast. And if you're just doing business as usual, at that time, what would happen is that we would probably got pollution problems, exhausted the natural resources. So this was started, the environmental indicator stuff, because the other ones started before, at about the 70s. And institutions like United Nations or OECD, just they were using them for understanding how all the countries were going on their politics. So in some way, they started with the idea of the sustainable development. So environmental indicators started with sustainable development. Then, of course, the environmental indicators are a lot of them. Like, for example, the number of people that has potable water, or, you know, something like that. For example, is also environmental indicator. We will not look at those in detail, but it's a kind of history. So the environmental indicators started, and the ecological indicators would be a group within the environmental indicators, okay? So just for you to know, the first system was using this type of indicators: the pressure, the state, and the response. So indicators can be divided whenever they represent a pressure. For example, the number of cars, it's a pressure on the environment. So there will be a pressure indicator. So all type of human activities, energy, transport, industry, agriculture, whatever you put numbers here, it's pressure on the environment. For example, the air quality would be the state of the environment, where the number of cars is the pressure, okay? So if you look to water quality, soil quality, water quality, you would get the state of the environment, and then you have a response. For example, the investment that industries do to control pollution. That is also a response of the society, and this is an indicator, the amount of money that you use to control pollution, or the amount of money a society uses to preserve natural species or biodiversity, whatever you can just put there, okay? So initially, those was the OECD indicators, which were divided between pressure, state, and response, okay? So they were the PSR indicators. Then we went to the European Union, and also the systems are using it. So United States also has a medium term between PCR and DeepSeer, which is this model. So here we tend to use the European one, which is this one. So besides having the pressure, they divided driving forces and pressure, okay? So they have these socioeconomical drivers which, you know, drive the problem, and then you have the pressure itself, which is the number of something that is causing a problem, and the state of the environment as it was before. Then we have the response, and then we have another one, which is the impact factor, which is the indicator of impact in ecosystems. And this is interesting if you just look at it. It looks that it's not very different from the other. But besides the driver, which is sometimes politics drive the pressure, so you can see behind the number of cars, if you have a law, or for example, taking the traffic out of the cities, that will be a different driver. Whether you don't have public transports. For example, if you don't have public transports, people tend to use cars. So that will be a driver, and the number of cars will be again the pressure, the air quality will be again the state of the environment, but then it's the impact on ecosystems, and that depends on the ecosystem. So ecosystems don't respond in the same way. And I always give an example. And this example is, for example, if you have air quality, during a long time there was this acidifying problems in atmosphere. So you knew that, for example, SO2 would give sulfuric acid and would be very acidic. And that there was a problem with acid rains in most countries of Europe, northern European countries. And for example, the pH of the water, of the rainwater, was a good indicator of that problem. But in fact, they could have different impacts if you have a granitic lake, for example, or a calcareous lake. So if the rain, the same rain, intercepts a calcareous lake or a granitic lake, will have different impact, because in a calcareous lake probably would be in the buffer capacity of the lake, so would not change anything, whereas in the acidic lake, probably would just get a very different number and will have a big impact on ecosystem. So in some way, this is an example just for you to think about, that the same quality, the same amount of problem doesn't have the same impact on an ecosystem. So for example, the increase in temperature will not have the same impact on an Arctic environment or in a Mediterranean environment. Definitely. So 2 degrees change in an Arctic environment could be the melting of the snow, which will cause a completely different pattern than, for example, in the Mediterranean environment, which is already very hot. Okay? Could also have big differences, but will not probably be the same impacts and the same. So we cannot measure things by the number of or the state of the environment. Just that. We need to measure what is happening at ecosystem level. Okay, and that relates to the capacity of the ecosystem to buffer all the situations, and also with the resilience of the ecosystem. So if the ecosystem has this structure and function quite well, it probably can have some impact and then back to the same state because it still has some resilient capacity. Whereas, for example, if you have a very simplified ecosystem and something happens and the only species that is doing that role disappears, then you can probably have a problem on that ecosystem. So it really depends on what you are receiving, okay? So those are the indicators that really matters for ecology, which are the impact in ecosystems. And most people, in terms of decision making, are only using these ones. So these ones will not have the same. Of course, they are important, so which is the temperature will increase 2 degrees. Okay, that doesn't mean that we have the same impact at ecosystem level in different parts of the world and different cultures, different economies. So this must be studied. So, okay, 2 degrees might have completely different impacts on different systems, and we need to understand what are those impacts. I would say that, for example, in Mediterranean, the increase in the minimum temperature will be the trigger point, and I would say that in the Arctic would be maybe different. I don't know the system so well to say whatever, but in the Mediterranean environments, having 45 degrees or 47 in a summer day, it's completely irrelevant for plant species that are there, because they already are much above that, a normal productive state. So they must be in some way in a situation that they can cope with that. Whereas with minimum temperatures, that's not like that. So you have a lot of diseases, you have the composition, which is completely different. So things in the minimum temperatures will be much important for the Mediterranean system during the winter than probably during the summer, for example. So this is just an idea for you to think about what would be the impact. So I think this is really important, and as ecologists, I really think that when we are going to more broader areas with environmental people just stay here, because this is really a difficult step. Because we need to find those indicators at the ecosystem level that help us to say to the decision makers what is the impacts. For example, people are using phenology. Phenology, you are the one with phenology, you are the one with phenology. Yes. People are using data from phenology to say how climate change is having a big impact, right? It's one of the examples that we should use, because those are examples that can help people taking this decision. So there's a lot of changes or not. People are just, they tend to say that there was no loss of species due to climate change. It's very difficult to prove that climate change directly caused the loss of species. There's a big debate about that. But for example, phenology is completely different. But we need to trace that for long periods, otherwise we are not able, because we have a lot of fluctuations every year. Unless we have really a long-term period, we are not sure if the trend is just noisy trend. Okay, so just please look at that indicators as the ones which are really important. And then with the Millennium Ecosystem Assessment, which I imagine that all of you already heard about, you have a slightly different perspective. So you have, this is the Millennium, so recently produced this type of indicators, which connect services with those indicators that I've showed to you. So in one side, they have the drivers, so the indirect, the driving force, the indirect variables, the direct drivers, the number of cars, the politics, So the state of the environment, and then at the impact, they have the ecosystem functions, okay? Which is, so Millennium Ecosystem Assessment focused on the services in order to put together things like economics, society, and the biodiversity. So their idea was we can mix up everything, otherwise we are not having trade-offs. Because if we lose okay, we can gain money with this, but at what price? So, and the idea is having ecosystem service in the same, this is the idea, which is really difficult to implement because most people are not implementing it anyway. But the idea is that ecosystem services, I think most of you are aware of that, are putting everything in the same sack and saying, okay, we will have money at the cost of 10% of loss of biodiversity, for example, okay? And so in some way, this is the idea. So what they made is they connected. And in fact, ecosystem services are measuring the impact, of course, because they are measuring the effect on ecosystem level. They are an approach at ecosystem level. So ecosystem functions will be impacted by this state of the environment, and though it will lose some functions that will change our provision of services. And then we can have a response as a society to change the drivers, to change the state, and then go back again, okay? And so impact on on human well-being is seen as this relation between the ecosystem services. I think that you are aware of the ecosystem services. If you are not, I can just slightly speak. Most of you already heard about it already. So this is really, although ecosystem services is a very attractive idea, people are not implementing in a way it should, because it's very difficult, because ecosystem services, in some way they rely on putting a price to everything, and it's really difficult to put a price on biodiversity, for example. And so when you put a price, it's always very low, and so people say, oh, this is not what I wanted, if you are from an environmental perspective. If you are from an economical perspective, you say, I pay to kill it, so, which is really also very strange. So I think we are still stuck on the money problem, but maybe even people can just, my idea is that you can use ecosystem services anyway, because you can say to someone, okay, you will have certain thousand of euros with that, but you will lose 10% of the species. And I think I hope people are enough clever to understand that losing 10% of species is complicated. So they might trade off between the number of species and not exactly putting some money on species, even without knowing what species they are, but just thinking about, well, I don't know, but just, I think maybe we don't need to go to the price tag, just to put prices in everything, because it's quite dangerous. Once things are a price, people pay it to do it, but asking people really if they want to lose that, to have that. So in different coins, I must say, in different perspectives. Okay, so this model interacts the subsea framework with the Millennium Ecosystem Assessment Framework, okay? So this is really important when we are going to decision makers. Sometimes we are just doing our research, but at the end we should frame it like that. Otherwise we are not able to communicate, okay? When we do our research, most probably we can end up with some indicator, with some information that is useful to society. And we should do it, okay? And you could frame it in this type of perspective. So as our decision makers and our international institutions and worldwide institutions such as the United Nations, they promote the implementation of certain rules, but then how can they measure if the money that is invested on that politics is really going in the right way? So people use indicators. So United Nations have implemented in 2009 several indicators that countries suffering from desertification should implement. They're still implementing it, so it's still under discussion, in order to every year be assessed and evaluate where people are just going on the right way or not, and the money is doing something different or not. Because sometimes you just put money in the problems, and the problems don't solve by themselves, but you need to be clever on the way you put the money. So this is what they are doing. So they need to implement some indicators of desertification to every country in order to be implemented and to make sure that the money was going on the right direction, so avoiding desertification and just recovering. So this is, I will speak about some of those indicators, the 11 indicators, and then I will speak more about the ones that make sense to me, which are the ecological ones, so about the biodiversity, okay? Because biodiversity is one of the indicators they propose, and then I will zoom down on biodiversity and all of that, okay? So, for example, this is the first, one of the first indicators is the poverty severity or the income inequality. This is, most desertified countries are poor, and as you know, probably drylands have a lot of people, so drylands, I don't know the numbers in my mind, but occupy between 30 and 40% of the world's area, and also have about the same amount of people living there. So they are areas which are in some way productive if you have water, but not productive if you don't have water. And so, and people live on the edge of that area, and when you get drier, people just get limited by that water. So this is really a problem, and you have a lot of people living in drylands with problems of poverty and income inequality, okay? So that is one of the indicators. And they propose, of course, the World Bank methodology and OECD methodology, since those are universal methodologies that are already implemented in the terrain, so that you don't need to change a lot things to go on this. Then another indicator they selected was the access to safe drinking water, which is another indicator again of how well, because water is the limiting factor in drylands, this is really important. And they also have these indicators. So I just have some graphs for you to understand. So the national poverty line and the Gini coefficient, which is a measure of inequality. And so if it's 0, so it's equality, and if it's 100, it's inequality. Like one people has everything and the others don't have anything. Okay? So this is as close as 0, it's better. And as you can see, I think they are. These maps don't need interpretation because they are really simple. This is what indicators are good for, because now you can communicate easily. What are the areas which are complicated? Do you want to make an interpretation? Some of you? Are you surprised by anything?
Surprised by you don't have data about Europe.
Sorry?
Surprised by you don't have the data about Europe.
No, well, it's because it's below 5% of population, okay? So don't have any problem. So it's because it's below that. So when it's less than that, so do you want to make some interpretation? Because the idea is that now it's where, if you just produce the maps, it's where you give it to decision makers, huh? It's the point where you just... What are you?
Argentina is very strange because there's a very low poverty, but still the inequality coefficient is quite high.
So it's quite high. When you say it's quite high, so if the coefficient inequality is quite high, it's bad, right? But
yeah.
It's still...
But still the poverty line is pretty low.
I don't know how they base the indicators, but it's on national statistics, and I don't know how they calculate the statistics. So, but you might have an idea sometimes, because that really depends on the governments producing the data, because this is reported by the countries. This is not assessed by an independent situation. So I'm not sure how the data, yes. So this is the things where probably they calculate in a different way. So I think even we have been this discussion in Portugal about poverty after the crisis, and there's a lot of big discussion, and people are using, you know, health NGOs. It was a discussion yesterday in the newspaper, and they were using the NGO perception or indicator instead of government, because you are not sure if they are manipulating the data. So they were using Caritas data to assess, so like, Red Cross and things like that, instead of government data, because they are not sure how manipulated could be the data. So maybe something like that. I'm not sure. But in some way, so you see, and if you just you have probably the dry land map on your head, and you see that's a superposition between national poverty and also inequality in the world. And that's really a problem. So most rich countries don't have they have problems of desertification, and this is like a feedback. So if you have money, you will not have desertification because you can combat it. If you don't, you will just things go wrong and you go to exhausting everything. And one of the problems of drylands is their variability in space and time. So drylands might have like a 20 years of rain where you just produced a lot of agriculture products, and then on the next 10 years it's really dry and you cannot take the same amount of food from that place. And this is really causing a problem because it's very variable in space, because it's suddenly you are on the other side of the mountain and it's already very, very dry. And in time, because during 20 years you were used to get that money from the land, and now you cannot get it anymore because there was a cycle of fluctuation of rain. This is really something which is really difficult to deal with, because this 30 years periods that are changing, and it's not easy to deal with this kind of variability. So other indicators that have been used by United Nations associated with desertification, and which I think is more related to what we like, it's the vegetation, land cover structure, and land productivity dynamics. So I just used, those are produced at global level using global cover and some other types of land at national level, or even continent level might be used in a different way. For example, Europe has this land use coding, which can be used for within Europe. It's very similar. I think states probably have the same. I'm not sure how in China or in Asia it's used. But we can have a look on the country level or at the continental level in some cases. But to the world level, probably we might use this global cover one. And also the dynamics, so it's about the productivity. You can have those maps of NPP, so of net productivity, for example, at the world scale using satellite images, where you can also address when there's a big change, for example, in deforestation and everything. So those are the maps that have been used at the world level. So just an idea. So those are the NPP, so the productivity, which is well at the tropical level, at the equator level, and then the changes in NPP every year. So this is an average of NPP change on the last, I think, since 2000. So where is the net productivity and where is the loss? So probably on those orange places you get loss of productivity. So those were other two. Then trends in carbon stocks above and below ground. So this is another indicator. So soil organic carbon stock or total terrestrial system carbon stock. So we know that carbon stock is one thing, and then the soil carbon is another thing. So most places, when even they are poor in biomass production, like drylands are poor in biomass production, they have a high concentration or carbon stocks in the soil. Normally, they store carbon for a long term. So there's this. So historically, they have these carbon stocks, and although they produced very small amounts, but they also, the turnover is very slow. So then you get carbon accumulated in the soil. So in some way, drylands are not very important in terms of carbon stocks for productivity, annual productivity, but they are important to the stored one, which is really the one that is important for climate change, for example. And
is this productivity concerned for the value or the amount of food? Or
sorry? No, photosynthesis, just photosynthesis. So drylands are low in productivity compared to tropical areas, right? In terms of productivity at the world scale, drylands are not very much, so the production is quite low. But the carbon is stored in the soil. So there's a lot of carbon stored in the soil in dryland areas, okay? Because it accumulates and the turnover is very slow, okay? But if things change in temperature or whatever, it can be a big change. So, for example, imagine that drylands get a lot of moisture, increase in relative humidity during the winter, or the winter temperatures go higher, then this carbon stock can disappear very easily, okay? For example, so this is, once you have a big carbon stock in the soil, you can change very quickly if you just have a big turnover, a decomposition, okay? So carbon is really important. Besides carbon, it's important for productivity. It's, of course, an indirect indicator of productivity of the system, because with carbon you also have other nutrients and everything. And then you go to biodiversity. And then what they do in biodiversity, they used, of course, biodiversity is a really problem because it indicates a lot of things at the same time, but it's really difficult to measure and it's really difficult to compare. So this is the problem. So this is where I want to start with the talk in terms of more specific. So this is one of the indicators they suggest biodiversity, and then they suggest global wild bird index, because this wild bird index is the more available at the world scale. I think it's because if you have the plant is more difficult to make interpretation of it, okay? So this is, birds are everywhere. Normally people that work in plants, I just say, again, birds. But in fact, everyone has assessments of birds in possible way, so it's very easy to do this. But what I think we need to do is to have a look on other components of the biodiversity, so plants and other animals, invertebrates, whatever, and also try to have a common partner at the world scale to compare. Because in some way, the way you go to the impact on ecosystem is in fact using biodiversity. Because if you just look, the only more close, so you have productivity, you have, but imagine productivity can be of exotic species or even invasive species. So you can have high productivity using invasive species. Doesn't give you a sign what is happening on the ecosystem level. So if you just use biodiversity and if you use biodiversity in the right way, we might have more information on how things are working and on the trends, okay? So this is the bird. So, and what we are trying to do in our group is in some way to find, this is just to represent a complex ecological system. So for example, this is about nitrogen, but don't look to the nitrogen, doesn't matter what it is. It is complex, so you have all this balance and everything. If you want to try to measure all the points, everything at ecosystem level, you would just get lost. I think even no money would allow us to measure everything. It's like in our health, if you just measure all the possible analyses you could have, would be a mess, okay? So we want just to look to some points, and those points are ecological indicators, indicators that things are changing or trending, and this is what we want to understand from the ecosystem level. This is really interesting to find those endpoints where things are changing. And this is the same as going to the blood pressure or to the cholesterol, whatever. So they are just signs or increase your risk of having a certain cardiac problems. Don't tell you that you will have, but you will increase your risk if you have all that triglycerides, if you have cholesterol, if you have high blood pressure. All of them indicate that. One of them just indicates something. So this is the same idea. Where are the cholesterol of the ecosystem? Where is the blood pressure of the ecosystem? So we want to find those points. And our hypothesis is that biodiversity would be a very interesting point to measure, because they would will affect definitely what is happening at ecosystem level. So this is, of course, there are other things we can do, but biodiversity would be our aim, okay? Although we also measure other things, huh? So those are just a definition of ecological indicators. So they are exactly as the other indicators. They are surrogates of something happening at the structure or functioning, composition or functioning of the ecosystem, okay, at whatever scale you want. So it doesn't matter really the scale. So it just tells you that it's a measurable characteristic trait of the structure composition or function of the ecosystem, okay? So you have, of course, exactly as the other indicators, you should fulfill certain requirements. You cannot just have, so an indicator should have, so when you try to find an indicator, you should look to the conceptual relevance of it, and it should always be relevant in terms of ecological function, and also to the assessment we are wanting to do. So you need to be practical to measure it, otherwise it would be just rubbish. So you need to have good data collection methods. So having methods already implemented, it's good for the indicator. The logistic must be easier, so you can have information management, quality assurance, and the cost must not be completely crazy. So you should have controlled costs on that, otherwise you cannot implement everywhere. Then you need to have a more, this is more a question, this is practicability, this is ecological relevance, and this is sometimes what we can measure. So does it change a lot with other things? It has a big error. How is the temporal variability? How is the cross-year variability and the spatial one? And how it discriminates against other things. So this is the type of thing that you have when you have an indicator. You should be testing these in different situations. And of course, it must be quite easy to make interpretation. And you have thresholds where you say, up till here the system is okay, after this the system is working in a bad way. And of course you can just need to be linking with management. Okay, so this is just saying to the manager, once this indicator gets here, you need to change this behavior, okay? So those are the typical, well, this is applied also for indicators, so it's the same, but applied with ecological ones. So they can be compositional, so you can have genes, tissues, species, populations, communities, ecosystems, functional, structural, or integrative, so like indexes. For example, at the riparian level, you can use very integrative indexes already, which puts, for example, the type of river with the type of vegetation. So you can just mix a lot of things in the same type of index. So you are using different indicators from different areas, okay? So those are already available, so probably already have crossed with that. Just to say that, of course, you get complexity when you have things at ecosystem level, and you have response times completely different. You have increasing difficult linkage between the stressor and the effect, and but the ecological importance also increases. So in terms of scale, you can use at the different scales. Of course, when you go to the ecosystem, it's harder, but it's more interesting anyway. Okay, so let's look at something which is completely different from our areas. So this is, for example, two indicators I took from European. Europe makes a collection of ecological indicators for climate change evaluation. I'm not sure. It's very interesting because they do very interesting things. This is, for example, from 50s till 2005. I'm not sure if you just see it. So this is 1950. This is 2005. This is the months, so it starts months 1, 2, 4, 6, 12. So imagine this is the calendar, and this is the years. So what you see is that this is phytoplankton in the sea. And this is, for example, chlorophyll, okay? The amount of green is the amount of phytoplankton in the sea. And as you could see, there was 2 seasons of productivity, very distinct, in 50s. And then now, it's a completely mess. You have productivity whenever the temperature is okay. Okay? So this is quite easy to understand, this indicator, right? So, for example, and this can be also specialized. This is temporal, this is spatial. Okay? So this was 50s, 60s, 70s, 80s, 90s, and 2000. So you just see all the productivity is much higher now. Sorry about. And this is an example of a very interesting indicator, very visual, and it's very easy to see that it changed a lot. So most probably the temperature here and probably the nutrients also in the sea might have changed during this period, especially because it's really around the coast. So, and then another example of an indicator, which are those this is a tropical fish, and this is so tropical. This is the, if you just, how can I just explain? This is 60s. This is 2000. Okay, so this is time, and this is latitude. Okay, and this is where they have been seen over the years. Okay, so what you see is those tropical fishes were seen most close to the equator, and now they are seen at temperate areas. And this is the places where have been seen at the same period. So as you can see, those are tropical fishes. With time, things change a lot. Although probably not, there was no loss of species there. There was just a movement. Those are really nice indicators, just examples of things that we would like to have to say people, you know, see, this is an effect. This is what I would like to have for terrestrial environments. I think aquatic environments are much easier because they don't do like that all the time. So we have like 10 years dry and then 10 years rain a lot, and then and the trend is really difficult. Whenever you get a 10-year drought period, you get all the politicians with you. Then starts to rain, and then they forget about it. And it's really hard because we don't have those graphs to tell them. It's really hard to communicate this and say, you need to be persistent on this politics. You know, you're just not, when, you know, had the first 3 years of drought and a lot of fires, and then, okay, so we're starting a drought. Everyone's just giving water to the populations, which is really when they are extreme, and then starts to rain when they start to increase and invest in this area. So it's really hard. So this is another example. So you have place and soul. So I don't know, but in Portugal, this fish is much more expensive than this one. I don't know. You know, place is this fish that goes beneath the water, yes. And then sole, it's a cousin, but it's much cheaper. I don't know if you all know, but in Portugal, sole is much cheaper than place. So like 2 times. I don't know if it's true or not. But just see the mean annual surface temperature in waters. And this is sole against sole. So it's the percentage of sole on the total percentage of both fishes. And you see the increase on that with the surface temperature increasing. So it's really hard. You see that we'll have only soles after some time, okay? So this, like that, so after this changing temperature. So this is something also that, this is taken from space. So this is time by space. So this is taken from different places with different temperatures. But in fact, if you just get high temperatures, you will probably have only sole if the temperatures increase a lot, okay? This is the sea temperature. So a 2-degree changes, for example, here has a lot of impact in economical terms for the fishermen. But let's say for biodiversity, because this is a biodiversity problem, just have an economic thing because it's sold for food. But this is mainly we would like also to have for plants, for example. Okay, so but besides, for example, climate change is of course also human impact driven, although we don't know exactly how much percentage is human driven, how much could be natural changes in the position of Earth against Sun and whatever. So we are not sure how much is due to man and to causes that are impossible to change. But in spite of climate change, we have all different drivers, all different changes that occurred on the last 50 years. So you have heard about Anthropocene, most of you, no? No, okay. So we have all these geological eras. So, Jurassic, I don't know, all the geology. Someone has known them all by Holocene. And then what people now call is the Anthropocene, because normally on that era you have glaciations and you have changes in temperature, and this is driven the biodiversity at a global scale and at a time scale, a millennium time scale, okay? But in fact, on the last 50 years, what is driving mostly Earth is not glaciations or changes in the position of Earth, it's really the man. So all indicators are like that. So it means that everything is being changed by man and they call it the Anthropocene. So it's the era where man has most impact and the geological effects. So it's some people, this is a discussion, but at least and all the type of indicators you get, even they are changing like that. So it's a really big change. Okay? And so this is they call Anthropocene. It's a nice paper. You can just have a look on that. So people and societies are the biggest drivers of global change. Not anymore glaciations, not anymore things at the global scale. For the global scale, man is the most influential at the moment. Okay? So in fact, we cannot go for ecological ecosystems without having a look on man. What man is doing it on. And I have heard about, for example, nitrogen. There was someone here looking to nitrogen, no? The impact of fertilization on something, no? Have heard? Fertilization? Yes. So, for example, we are producing since, you know that Malthus, you heard about Malthus? Malthus said in 19th century that probably we will not be anymore in Earth because it was not possible to produce food for everyone. The curve of Malthus, you've heard about it probably. So what happens is that there was the invention of the Haber-Bosch method, which allows us to take nitrogen from the atmosphere to produce fertilizers. After the Second World War, this discovery was on the end of the 19th century, but was most evident and most clear after the 50s, after the Second World War. And for example, this is a big change. Everything we have in the Earth at the moment is more fertilized than before because we are emitting, for example, NOx from the cars, which transforms in nitrate and it drains with nitric acid, which fertilizes all the world, including the Arctics, because it goes around. And ammonia from livestock, NH3, for example, it also fertilizes everywhere, everything. So you have, for example, if you have oligotrophic plants, rare plants, most probably they will get lost in the next years because we are fertilizing all the world. Okay? So this is an example how man is influencing everywhere. Besides, you know, that for example, people in the Arctic, they detected lead, organic compounds like DDT and other PAHs, PCDD. So they detected a lot of compounds in the Arctic where there's no human activity there. But, you know, with the atmospheric circulation, it goes there and deposits there. So everything is being transformed and being changed. There's a lot of metals in the atmosphere, in the soil. Even with lead that stopped, for example, being emitted in the cars in Europe, we still have lead in the soil, which changed completely the pattern. So we've increased the 2 times or 3 times more lead. This is not was the usual stuff. So this changes the competitive patterns between plants, animals, and everything. So these are changing things a lot. We are not being aware of that, but this is in fact changing a lot. Okay? So all this Anthropocene is our background at the moment. So even when we want to do climate change or whatever, we need to say it's temperature with nitrogen, with pollution, with whatever. It's just a lot of things together, which is even more difficult to measure. Okay? So for example, now it's really difficult to get very clear air from nitrogen. Nitrogen is being influential everywhere. Okay, so there's a lot of global changes. So this is an example. This is from the Millennium Ecosystem Assessment. This is the type of biomes and the drivers that can change biodiversity, okay? So we have habitat change. In the past was very important. People destroying habitats for cities, for industrial areas. So they were changing the land use. In most areas, this is not any more important. So those are the drivers were important on the last century. Those are the ones that will be important in the future. So not in, for example, if you go just to Mediterranean areas where we've been here, so there was a big importance in the past, not so much in the future. For example, climate change was not important in the past, will be important in the future. Invasive species were important in the past, will be important in the future. Overexploitation, collection, so for example, killing the animals and do that collection was important in the past, but not anymore in the future. But pollution from nitrogen and phosphorus will be very important. I'm not sure, this is the Millennium Ecosystem Assessment, saying the threats, the past threats and the future threats to biodiversity. And this is planet boundaries. Have you heard about Rockstrom paper in Nature? So this paper was produced initially in Ecology and Society and then in Nature, where he just analyzed a series of variables, like, for example, phosphorus cycle, ozone, ocean acidification, climate change, chemical pollution, biodiversity loss, and he evaluated what would be the thresholds, the tipping points for having influence at a global level, and putting in cause our sustainability on Earth. And he found that the ones that already overcome the threshold was the nitrogen cycle, changed a lot, and no one speaks about nitrogen cycle at a politician level. So this is really, really important because it's homogenizing all the world. So we are losing species without controlling that because everything is getting fertilized. And so if you get fertilized, no oligotrophic plants exists. So most rare plants are oligotrophic, okay? So those will, be full of plants that are nitrophytic plants. Of course, biodiversity loss and climate change. So chemical pollution, they don't know exactly what will be the impact. So this is, for example, global change drivers that can affect the planet. And for them, those two already passed the safety boundary, which means that we will die because of those. so we will not have sustainability on Earth because of those. Anyway, this is under discussion. There's a lot of people going for planet boundaries and having this type of, where is the thresholds, where are the planet boundaries, what are the factors that will drive our unsustainability. Anyway, this is for discussion. Both papers are very interesting. You can have a look on that in the future. Okay? Oh, okay, it's already. And more. So when we look at ecosystem level, we are ecosystems in some way, we need to evaluate their sustainability, okay? So they are affected by those drivers. And we can have things like this, for example. So, for example, I'm thinking about, let's think about again desertification, because I'm trying to put desertification among the other things. In fact, desertification can be worsened by climate change, of course. If climate change gets the areas which are drylands at the moment even more drier, which is what they expect to happen. And for example, deserts are more quickly, they happen more quickly than thought, like Sahara or Sahel or whatever. They change a lot in a few years, of course, in big years, but not as slow as we could thought. And what happens at ecosystem level is, for example, imagine that is a drying period. So, for example, this is the driver. Let's see, for example, precipitation decreasing. And what happens is, for example, imagine productivity. So we have, for example, productivity. So what happens when you have linear tracking at ecosystem level is that we have low precipitation and we have also low productivity. And when we look to these two things, they are linear like that, okay? If you just put those two things in the same graph, they have this biological response to the driver is linear, because when you get lower precipitation, you get lower productivity, right? Clear? Okay, then you have the system where, okay, you have, for example, increase in temperature, and then you have a decrease in productivity, okay? So, but a small increase in temperature caused a big decrease in productivity. And this is what we call nonlinear thresholds or tipping points, okay? Nonlinear phenomena, which we are really afraid of, okay? Which is a small amount of extra temperature, which is apparently linear, cause a big change on the response of the ecosystem, okay? And those are the famous tipping points, okay? So when we look to these type of things, so when we look in time. But even we can have this type of response, which is low productivity, but then again we decrease the temperature and things go back to the normal state, okay? This is reversible. However, there are others, well, there are other cases where you have hysteresis where you don't have recovery. So temperature goes back to the normal, but the ecosystem don't go back anymore. So it will have like a scenario like that, okay? So we'll just go down always independently of the temperature. So in some way, there was this irreversible tipping point, which is really difficult to overcome now. So this is mostly what we are also looking for. So how does ecosystem changes over time? Does it has a linear behavior? It has a tipping point behavior? Where is a tipping point? Can we have early warning indicators of that? Can they be ecological indicators? Because it can happen like that, and then it's irreversible. So, and we want to have a look on those early warning indicators, okay? So those are the things that we have looking on our things. So the tipping points, what we are looking for now is early warning indicators, so things that happen here that don't allow us go down, okay? And what we think we would like to say is that we know that our rationale of the thing is that we have diversity is related with ecosystem function, okay? So if we look to diversity, we can have a good indicator of ecosystem function. Ecosystem function is quite related with ecosystem services, because what is on the basis of the service is the function. So for example, nitrogen fixation, productivity, it's everything, it's related with biodiversity, okay? So functions are related with the biodiversity because it's related with the traits they have. If you have fertilizing plants, plants that fix nitrogen, they have fertilizing functions. If they have a lot of plants that grow fast, traits, they have productivity, okay? If you have a lot of microorganisms, you have decomposition, okay? So balances within the ecosystem, functions in the ecosystem are related with biodiversity, which are related with the traits. And so if we have the traits, we can go for ecosystem services directly, okay? This is not only me saying, this is a view of it. So ecosystem services are really to value biodiversity, okay? They were made to value biodiversity. Although some of the services have economic value, some of them don't have economic value. That is the only difference. But they are all based on biodiversity, okay? So we can have also global change effects. So our idea is have a look on that biodiversity as a way of looking to services, okay? Okay, so this is a colleague's work. And this is, in Portugal, we have oak forest, native, very beautiful in Gerias. You must go there in the border with Spain. Very, very beautiful. It's our most wild park. Then you have pine forest, which was planted 500 years ago. We don't know if it's native or not, and we just feel it like, okay, it's ours because we have pines everywhere, but pines are not the perfect dream ecosystem. And then we have eucalyptus, which is from Australia, completely exotic species, and we don't like eucalyptus in general, as ecologists, of course. I'm just saying it in a very way. But then we went to birds, say, oh, birds will have low diversity here, more or less, yeah, and full of diversity here. But it's not true. So, sorry, it's just going faster. If you look to birds, for example, 30, 40, 28, how can it be? So, those very nice native, almost the most wild place in Portugal, has less birds than the eucalyptus, and pine trees have more. We just got, this is really bad. So how biodiversity can be an indicator? So saying that eucalyptus is good, that is not true. So we know that it's not true. So what is the problem? So, okay, does all the species have the same value? And this is the point. So if all the species have the same value, then you have ecosystem process and biodiversity. We lose one species, we'll lose one function. We'll lose one process, okay? And we'll go like that. If the species is redundant, so for example, nitrogen-fixing species, we have 20 nitrogen-fixing species, and if you lose just one, there's a 19th still functioning, no problem. But if it's a keystone species, the only nitrogen-fixing plant species, then we lose nitrogen function. Okay, so all the species don't have the same value at ecosystem level. Depends. Of course, there's the species that depends on the ecosystem. If it's a lot of rain, it's not important species, but if it's dry, it's an important species. So it depends on the environmental conditions and on the trade-off. So those are more complicated to address. Of course, we need to simplify it to explain it, but it's, of course, different. But keystone species, species that are really the only one doing that function, are really important if there's only one species for that. So we came to this concept of functional diversity, which is much more broad than just number of species, which is everyone using. Number of species can be just exotic species. Let's count species in a town. We'll have a lot of bird species in a town, but they all will be pigeons and, will be, species that have a value, but they are all not representing all the spectra of the functions that they can do. Okay? So if we have, this is a species richness as function of functional richness, okay? For example, if you have like that, a lot of species richness and very small functions, then species overlap in functions. So we only have 4 functions, but we have dozens of species because all of them have the same function, okay? But we can have like that, one species, one function. So all the niches is occupied or superimposed, and of course this is just a diagrammatic way of doing it, but most of the niche is occupied. So one species is representing one function. Or we can just have, for example, a lot of functional species, functional richness, and low species, which is intravariability. So species, not only they represent one function, but they are, for example, phenotypically so different. They can represent different functions at different spectra of the gradient because they are really variable. You have those species that are everywhere in the world. They don't look the same because they are phenotypically so different, okay? So this is the kind of places where you can get this type of interspecific variability and also have a lot of functions with low number of species, okay? Why functional diversity is so interesting? First, it relates directly to the functions, to the process in the ecosystem, so to the services, okay? So it's much more closer to the services. Second, it's independent at a world scale. So nitrogen-fixing species, it's a word that everyone in the world understands. But if you say trifolium, who is working with trifolium? You. Say it again, the species name?
Subterranean.
Yeah, probably everyone has that one. But imagine another one. There's a plantago, a rare plantago, which is a plantago in Portugal that no one has. So how could I just say what function does it represent? Because, this is just a name. So I cannot match the species names, but I can match the function they work. So if they have, it's a nitrogen-fixing plant, they will have that role, but besides that, other roles. But that role, it's universal. So we can compare diversity, functional diversity at a world scale, which is our interest because we want to have indicators at a global scale because we have global change factors at the moment. We cannot just look to our country, okay? So those are really the importance of functional diversity. So the way to do is, okay, we have biodiversity, ecosystem functions associated with the traits, so we can have regulating service, supporting services, cultural provision, human well-being. And we can do it like that. Biodiversity is the building blocks. So I would say that leguminous plants, just looking at this XM example, is the building blocks. Okay? Then ecosystem function is the factory, which is the nitrogen fixing capacity. So that is the trait. Then ecosystem service is the product, which is nutrient cycling, which is the service. And then human well-being is the food production or the soil quality, whatever you want. Okay? So we can do it in that way. So we'll go directly to services by this functional approach, okay? I think I'm doing my Portuguese time, so please tell me how many minutes I have because I have 9. Sorry? 40? 40, still 40 minutes, 40 minutes, okay. Okay, you know what are drylands, so this was just, okay. Then I also like I'm just looking now to our work. So I will go to our work now directly. So our hypothesis is that functional diversity is much more interesting to evaluate ecosystem services and as indicators of desertification than other measures of biodiversity, okay? So we are working on drylands, as you all know, by this time. And I really like this map because this is a triangle of temperature, sunlight, and water. So if you look to this map, you will see what is limiting the productivity in every part of the world. So, for example, here it's sunlight because you have a lot of water, the temperature is perfect, but you have a lot of competition for light. But in other places, of course, it's temperature. In other places, water. So for example, water somewhere here, water here. So what is limiting productivity and what is the factor? And it's very interesting. I think this triangle is very interesting to have this idea of what is limiting productivity at each place. It's just... Sorry? It's with no productivity at all. Okay. So no productivity, nothing is growing there. Or at least that they measure at that level, okay? So what we want to do as an overall project, and we didn't reach that point, is going for early warning indicators of tipping points in terms of desertification. So because we don't have time for 50 years research, what we are doing at the moment is using space for time, okay? So we are looking at space to see the time, of course validating whenever possible with time, but we will not have 50, 30 years of time to get these results, but we need to be very cautious because some of the things don't happen at the same level. So our hypothesis is that functional diversity is more important than total diversity as an ecological indicator because it's connected with ecosystem functions and can be universal. And we will go for plants and lichens. We have worked with plants and lichens and at several scales, okay? So what we have been doing is, I already explained this, so I don't need to do that again, is looking for functional diversity for ecosystem process and ecosystem services, okay? So it's just an example of functional traits, ecosystem process and ecosystem services. For example, shoot age or wood density or lifespan is associated with accumulation of standing biomass, which is associated with carbon sequestration and climate regulation, or leaf nutrient concentration with net primary productivity, soil formation, fertility, food and fiber production. So those are some of the services you might associate with some individual plant traits, for example. And some plant traits, of course, interfere with several other services in a different way. So this is just Portugal. Portugal has a high variability in climate, just for you to know. We can have 3,000 millimeters a year, a lot of rain, and we can have also 400 around here, which is the driest area. So we have high variability. It's a very small country with high variability. This is plains, this is mountains, this is high property, this is low property. So that's why we have a lot of wine, cheese, food, and everything. So everything is quite variable. You have completely different cheese, completely different wines from one place to the other because of this climate, okay? And of course, the climate change determines the landscape. So one of the important landscapes which I want to introduce you is the Montado system, which is a savanna-like system. As you can see here, it's a kind of savanna based on two types of trees, Quercus schuber, cork oak, and Quercus ilex, olm oak. So half of the country, which is more humid because of the sea, because the winds are like that, have Quercus schuber, and we just take the cork, and we are the highest cork producers in the world. And here it's more dry, and it's very interesting because Quercus ilex designs in some way matches the driest areas and the dry lands in the country. So Quercus ilex is on the right side of the country, okay, which is drier. And this is just an example. So Montado is a multifunctional landscape because people take cork, you can have wild pigs, you can have aromatic plants. So they provide a lot of ecosystem services. They provide money for the people, but a high biodiversity value because you have a lot of birds. This is a co-evolved situation. Europe is completely transformed by man. There's no wild landscape anymore, wild. So everything we have is, of course, influenced by millennia of man occupation. And Montado is a kind of co-evolved situation where you have a high biodiversity value together with high revenue for people, and it's a really high, it's important landscape till if you if the cork has value. So if you start to drink wine with plastic lids, you are destroying our south of the country. So think about it, okay? We are destroying this system. This system works because the cork still has value. Of course, cork has value in different ways, but still the lids of the bottles are the most important one, okay? We have LTR study area in the country. So we have long-term ecological research sites associated with Montado system. So if everyone wants to compare the system, this Montado, and with their country, for example, in Greece or in Spain or in Italy, because they also have Quercus ilex, you are welcome, because we have these stations, in all these stations around the country in different areas. So as you can see, in different climatic areas and with different types of management. So it's, we are available to receive some students in these places, okay? And so our study area was developed on the semi-arid area. So as you can see, it's looking at these gradients. So we have about 60 sampling points where we've measured all the plant biodiversity, okay, assessment, herbs and shrubs. And you will know two persons, Alice and Melanie, which were responsible for most of the sampling. Tomorrow they will be there. So Alice will make a talk, and Melanie will also be present at the workshop in the cost action, okay? And what we do with the plants, so we do plants as people, as usually we just point intercept method. But besides that, what we use at the end is just we have a list of species, and what we do is just we fill the traits. Then we do a database of traits for each species. Some of the traits are from bibliography. Some of the traits were measured, like 8 were measured, and you know, types of leaf, the leaf specific leaf area was measured. But some of them were just, you know, the flowering period or something like that, because we didn't have time on the field to observe that, were measured from herbaria data. So sometimes, of course, if the species is well known, it's good. When a species is so not well known, it's not so good. But we do it for 80% of the community, which reduces a lot. So we are not looking for rare species. We are looking for services. And services are performed by species that cover most of the area, okay? So we are not looking for rare things. And we used metrics such as functional diversity metric, functional divergence, and everything. Then we can have more details about that. So when we had our gradient, so we have about 60 points over the Alentejo in a gradient of desertification. When we looked to the data, we saw that our first filter was soil. And then, I don't know if you will know Eduardo Constantini, but you probably will know on the workshop. Eduardo is a soil scientist. And in this way, we have little soils and alluvial soils. And what happens on alluvial soils is that those, because they contain more water, they retain the water during a longer period. They work like they give more time available, the plants have more time available to take the water. So those soils are like, it rains and that's it. No more water available probably. So this is the first filter, which is not climatic, but in a certain way is. And Eduardo, very interesting, developed an indicator of aridity, which an indicator of aridity only based on atmospheric phenomena, okay, temperature and precipitation. Whereas Eduardo developed this indicator which adds the soil component. So if the soil holds water for longer periods, plants will have more water available during more time. So even if aridity is very hard, it will take longer to dry. And so we just make like, it adds this component of the soil to this indicator, which I really think is really good. So this indicator, which is aridity, which is the indicator that the United Nations uses to measure aridity everywhere, together with the soil, will be a very good component, because we know plants. So plants, in some way, they correlate well. So this is the traits we've measured. And in some way, they all correlate well together with the same points, but we know that they behave in different ways depending on the soils, okay? So soil was the first filter. Independently of that, so there was some traits that were really influenced by the gradient of desertification. So life cycle. So life cycle, what this means is not necessarily that there's a gradient. This means that when you have a positive correlation, you have more traits than with when you have a higher value of functional diversity, you have more variable of traits. So you have annual, biannual, perennial. Whereas when you have, for example, lower number of traits, you just have annual plants, okay? So what we are looking is diversity of functional groups, diversity of functional traits, okay? So for example, here you have life cycle, seed persistence, specific leaf area, dispersal mode, 8. And though some of them are remain in the little soils, and also there's another one like onset of flowering, duration of flowering, nitrogen fixing ability are only true for the more wet soils, because then we don't have so many plants like that in the driest areas, okay? So if you just look point by point, just an interesting thing, those traits are for survival, and those traits are for living and lasting. So if you look, this is the lowest desertified area here, so where you have alluvial soils. And means that here you are able to try to live and last, whereas here you're just trying to survive. So it's very interesting that it separates the traits in these two ways. So if you just look, for example, for life cycle. So aridity index, it's the opposite. So here it's drier, it's wetter, and this is drier, okay? So it's in the opposite way. Sorry about this. It's an aridity index, but the reading is very hard because you're always looking to aridity in this way, but not. So aridity is on that way. Aridity is here, okay? And what happens is you have diversity of functional traits here, where the aridity is lower, whereas here you only have few traits, okay? So this is most of the traits. So life cycle, and life cycle relates to carbon sequestration, water regulation, soil formation, and protection, food and shelter, for example. This is nitrogen fixing ability. Again, we have more nitrogen fixing ability capacities on the right side, so we don't have aridity. Duration of flowering, the same. So we have more variability of traits when we don't have with low aridity. And of course, duration of flowering is related with pollination and seed dispersal. And for example, even aesthetics could be related to the people like flowers, and people can like some flowers. So those could be related with that. So in resume, just to say that we have traits that are influenced by desertification that we found in Portugal, that have correlations with functional diversity and aridity. So those traits were related, and those were the ecosystem functions we could associate. But besides this, as you could see, these are universal traits. So it would be very interesting to know, for example, in your countries, if those traits are working the same way. And we are trying to do this with Lena. So we already are developing a kind of protocol. So in this case, for example, to see how much we could do this, because then we can apply this methodology everywhere if people have biodiversity, if they have measured already biodiversity, and if they have good databases of biodiversity, then we can do this, okay? So just to finish, if we just plot all that functions together, so you have the traits separately, okay? If we just put all the traits together and we plot this functional diversity of all traits together, what we get with aridity is this phenomena, which is nonlinear response. So we get a different behavior, and in this different behavior, what we have a loss of functions when we go from subhumid to semi-arid areas, okay? Which are also related with productivity, etc., and etc. So clearly, this apparently could be a good indicator. Functional diversity in overall of the traits that respond could be a good indicator, for example, of desertification gradient in space. We can try to prove that in time over time, so we are not sure that it will work on time. And this could be applied everywhere in the world. Doesn't need to be only in Portugal, because it's completely independent of the flora, and it's just a function, okay? So, oh, by the way, this is taxonomic diversity. It doesn't have any pattern, which is what United Nations are trying to promote. Because there's no relation between taxonomic and functional diversity here, in this case. Doesn't mean that it works everywhere, okay? Because sometimes some authors say that taxonomic diversity is quite connected with functional diversity, but not always, because it can be redundant, for example, okay? So those are the conclusions which are already said. And if you just look to lichens, because I started with lichens, so I never leave lichens. So if you just look at lichens, Lichens, it's very similar way. They are poikilohydric organisms. They are a symbiosis between a fungi and a algae. And they are everywhere in the world, from the Arctic to the deserts. They occupy all the biomes. And because they are poikilohydric, they respond to climate change, because they respond to the differences in water availability in the air, which is even more broad than soil. They don't have the problem of soil. It's good because we can look at them. So we just made a kind of same methodology. So instead of measuring lichens on soil, we've measured it on trees, epiphytic lichens, so they respond to the atmosphere. And we calculate a kind of measure, which is an indicator which connects cover with species diversity, exactly as in plants, okay? And what we do is measure functional traits exactly on the same way, okay? And we looked, for example, what are the traits in lichens that could be interesting? For example, the type of photobiont. Photobiont is the type of algae in the symbiosis. And it can be a green algae, can be a trench poly, which is tropical, and can be a cyanobacteria. Cyanobacteria, it's very interesting. It only photosynthesizes with liquid water, whereas those two can photosynthesize with vapor water. So this makes a big trait difference, okay? And those, for example, the green algae with trench polia needs to photosynthesize with higher temperatures, so it's tropical, okay? Whereas another type of trait, growth form, so for example, crustose lichens, those three-dimensional lichens that we can see very easily, folios like leaves around the tree, and then crustose, which are in the stones and in the trunks, which you don't almost see. And then reproduction, so they can have different types of reproduction as well. So you have some traits you can easily identify even when you don't know the species. So you can see those traits even when you don't know the species name. And so what Paula is doing, which is a PhD student, is looking to this. And what she built, for example, this is a microclimate effect, just for you to have an idea. So this is a mountain. This is a north-facing area. So you are exposed to in a different way, so as you can see. And when we look to the potential solar radiation, in this case, so sorry, this is a south-facing, let me just have a look. No, where is the point? Okay, it's like that. So this is the north-facing area. This is true. So this is the north-facing area. This area is like connected like that. So if you see, potential solar radiation is a variable we took from the GIS, and it's the amount of energy that can potentially go there without any clouds, okay? So imagine that there's no clouds, and then you can have this energy. So this type of place will be shadowed by the mountain. So what happens is that here you have more energy, here you have low energy. So it's, and this potential solar radiation is like an indicator of microclimate, okay? So you have this idea. So when you look to lichens, what we saw was green algae lichens were dominating in that area and green and cyanolichens on that area. So this must be mist shadow because you need liquid water to have photosynthesis. And this is another area here where you have more photosynthesis. So in some way, they respond in a different at a small level. So at the mountain level, they responded to potential solar radiation in a way that cyanolichens would be in more shadow areas and green algae lichens would be in more exposed areas, okay? So when you look to a correlation like that, you see those kind of differences. So for example, even in a small area, looking at lichens and the proportion of lichens to each group, you can see whether you have a microclimate or another microclimate. You distinguish all the microclimate because they are able to reproduce this at even a microclimate level, okay? So Paula made this in the Iberian Peninsula for now at a macro scale, okay, looking to the same traits. And we found a very interesting phenomenon. So with the aridity index, we get a multidimensional scaling with lichens, which I think I'm just running a little bit because of out of time, but I can. So she made multidimensional scaling, okay, where she put all the different functional groups. She identified the first axis and the second axis of this multidimensional scaling, and then she projected the first multidimensional scaling against aridity, and she saw that there was like a gradient also. When we plot this area, which was changing, so this was quite stable, and then suddenly there was a change in the relation between the axis 1 and the aridity, what we found is this one. So everything, this is like early warning of desertification at the Iberian Peninsula at the moment, using lichens that we measured, and then we predicted for that area. And if you look to the aridity index, it's quite similar for the region. So what we used was the change in functional groups in lichens to understand where was the trigger point in aridity, and then plot that point, which is resembling very much the aridity index in the area, okay? So then we are doing this. Oops. Okay. We are doing this not only at the Iberian Peninsula level, but also at other levels. So she studied also in Brazil, Thailand, and other places in the world, and United States. The data from the United States is not yet here. And so we are doing this in a kind of lichens we easier to universalize because they are easy to sample. So what we've done, we'll apply this knowledge of the functional groups to all the places in the world, okay? Including the Brazil. So for you to know, just for example, this is in Brazil. This is Amazon, so tropical forest. Then the interface between tropical forest and Cerrado. Cerrado is a biome which is dominated by fire. So it's the other biome after the tropical forest. And then what you can see is, for example, crustose, foliose, fruticose, and leprose lichens. In the case of crustose, completely changing. So crustose lichens dominate in the tropical forest because they have very low light. But as soon as we have open canopy, they will change completely against foliose lichens, for example. So we have promising results to apply these also for different places as tropical to desert, okay? The idea of functional groups as indicators of climate. Okay, but this is always in space, and you can tell me, okay, but it will not work over time, because time is completely different, and in fact must be different. We don't have time to search for indicators over time, but we can select some indicators in space that we can just try to see how they work over time. And we have an example. In Portugal, I'm doing a sampling here since '92. This is a mine site. And they have been asking me to monitor this mine site, and I started my PhD here. And luckily, they have been asking me every 5 years to do that sampling. So the mine is, polluting like 2 kilometers around, but I'm doing always a 7-kilometer sampling. So I'm much away from the pollution, and I sample always the big region, okay? So since '92, I've been doing this sampling. And suddenly, there was an year, 2005. We don't have the data here, but it's the same. After 2005, suddenly a big change occurred on lichen diversity on a group which called Trentpolia. Don't see it here. So Trentpolia, how were those lichens that were tropical, that I've told you were tropical, had the algae which was tropical, and that only occurred in places they occur like 50% or 70% in tropical areas, and they were only occurring 2% in Portugal when I started my sampling. Then suddenly, it started to 12% of the population. And we said, wow, what's happening? Are they just getting, tropical in the Alentejo? And Alentejo is really hard. It's 45 degrees in the summer. It's really, really dry. And it's more continental. And then this sudden change in time was really surprising for us because we've been doing that for a long time. We had the list of species, and suddenly it didn't work out the same species. So we said, wow, what's happening? And then, interestingly, at the same time, we had Alqueva. Alqueva, it's the dam, and it's the biggest dam, the biggest mirror of water in Europe at the moment. So it's kilometers and kilometers of water. It's not very deep, but it's very large. And you see, this is a satellite image before 2002 and after 2003. So between 2003 and 2006, this dam filled up. And that's where we got this difference. And in fact, we went to the closest climatic station and looked for relative humidity. But the relative humidity trend was like that. I said, it was not relative humidity. So it was not that. But then we said, okay, let's look at some indicators. And so the trend probably is the same. So we just looked to the number of hours with more than 95% relative humidity, because that would be relevant for lichens for photosynthesis, almost near condensation. And look at this pattern. So it increased a lot also. So in fact, there was increasing from 5% to 30% in the number of days with more than 95%. So we should cut it here, the number of days, the number of hours during the night, because lichens will not be able to photosynthesize during the night, but with this indicator is more than enough to show that there was a big change in humidity in the region. We are not sure if it's really them, if it's just climate change, because with increasing temperatures in the sea, you get more relative humidity, you get higher moisture in the air. So I'm not sure what is the cause for this change in humidity, but the lichens immediately reflected that. That's an interesting thing. So in fact, for example, people don't look at relative humidity in normal trials. So when they look to the climatic data, normally relative humidity is just left and it's just an average. They don't look to this tipping, to these areas, to how many dry days, how many wet days, and they don't look to these type of things that really make differences for biodiversity, for example. So this is, apparently it works over time, okay, for lichens. And with plants, we also already have 5 years of sampling, and it also works. Functional diversity works for plants. It's a really, it's Alice's PhD data. So she's doing just, which I have this idea where I didn't treat the data completely at the end. But what we have is taxonomic diversity changed a lot, but functional diversity remains quite stable. So apparently it is a good indicator over time because it doesn't change. So if you have a wet year, diversity is completely different from another dry year. But the functional diversity doesn't change. So it looks like apparently functional diversity will be a very good indicator for trends over time also. But we just have 5 years of that, whereas here we have 20. So it's different, okay? Just to say, how many minutes do I have now?
A quarter.
Okay. Just to say that, of course, that we, it's very interesting to do biodiversity assessments, and it's really nice to have this data, but it's really expensive. And if I was going to United Nations saying, let's do it everywhere in the world, they would say, you are crazy, because those were poor countries. How do we want to just, they don't have any biodiversity assessment. They would not do that, definitely, okay? So you need to have a cheap solution, and at least a solution which you can just look at places and then maybe go there and do something. Okay, so this is the only way is remote sensing. And remote sensing, we need to use more remote sensing. So we need, but as we were saying in the Portuguese training school for the ones who were there, we need really to calibrate with real data, not just doing remote sensing and just say, okay, we've done it. We need to do it and be able to work with people that are going to the field to make sure that it's really doing, making sense. Otherwise, everyone is working in a separate way, and no one is doing like that, and it will be terrible. Because people are buying remote sensing work because it's much cheaper. But if you don't calibrate, they don't have any value. And also people from taxonomic work says, I don't work with these guys because these guys, I'm taking my job. They will not go to decision makers. So it must be like something like that, okay? So people from remote sensing must work with people from taxonomic work, otherwise will not go further. And I think that will be there will be work for everyone then. Okay, so we have this type of landscape. So we have a gradient. That gradient that I was talking about in Alice's work comes from a dense woodland, then montado system, which is much, much more open, till open areas, okay, where you just have grasslands, which were used for intensive agriculture. Were like that before, but was for intensive agriculture and remain like that. And so Pedro, another person that some of you met in Portugal, was looking at this at the landscape level, okay? So he just sampled all these points that are in black were sampled by remote sensing. So he was using the National Forest Inventory, okay? And then also using NDVI from remote sensing images. And as you know, you have this. You have the spring, where you have high NDVI. Then you have the winter, and the summer. Sorry, where you have lower NDVI. So here you have highest productivity. Here you have September, where no productivity. So these are the perennial vegetation. Okay, this is the annual vegetation, right? Okay, so we can have a look on this and making some metrics based on this. Okay, and so just what this is every month NDVI, and this is everywhere in our landscape, the highest and the lowest. Just I forgot to tell you something. For example, a very dry year. You notice very well, right? This is completely different from the others. Very low productivity, okay? So you see the maximum and the minimum all on that landscape, so all that landscape, okay? So you see the variation. What we've done, we looked at the curve and we make an interpretation of the curve, okay? So for example, if you look, this is cutting, can you just go down a little bit? No, it's not possible. So season starts here on point 1, okay? And season ends there, okay? So that will be the season length. This will be season length. This will be the rate of growth of vegetation, and that will be the rate of decayment of the vegetation. That, in terms of season length, so all ecosystem productivity will be everything in gray. All this gray will be ecosystem productivity. And seasonal productivity will be this only annual productivity. Okay, because this is shrubs, perennial shrubs, and trees. And then senescence rate will be that one, and there's something else missing. Well, I'm not sure when. No. Just. Oh, base level. Okay, so we have this base level here, which is like the perennial productivity. Okay, we just measure every perennial productivity also. So we can do a lot of statistics with this because we have thousands of points in that area. So there are things very interesting. So in terms of all ecosystem productivity, so for example, there's a lot of differences on the season start date. There's a big variability, for example, here, but just we can have a look on the data. So for example, especially if you look to the specialization of those indicators, we can see, for example, whereas, for example, red in this case are lower values and blue are higher values. So those are the driest areas. And this is a mountain close to Algarve, so which is much wetter. So you can see that, for example, here, those areas in blue we have more perennial vegetation. Those areas here are which have, for example, with seasonal end later. For example, areas like that, where we have the season ending later, and areas like red, we just have the season ending on the day 165, which in the year it's like April, May, something like that. I'm not sure. So those will be ending faster after the growing season. And the season length, so will be again shorter in those dry areas, okay? So this will be very nice because you have like a phenology of the ecosystem, okay? This is a phenology of the ecosystem. Okay, so what we just divided these on, we call it productivity variables and phenology variables, okay? And then we related that with long-term precipitation and concurrent precipitation. So those started on 2000 till 2012, okay? So we just relate that variables with those 12 years of precipitation and with longer-term precipitation, which is 50 years precipitation. And interesting, we found better correlations with long-term precipitation, as if the ecosystem has some kind of legacy of memory, which makes the response dependent on the precipitation, but also on what happened in the past. And I think it's quite interesting that, of course, soil is a very important legacy, because soil is there because of the past precipitations. Soil is rich if there was good past precipitations, or soil is poor if there was lower precipitation in the past. So soil might be associated with legacy effect. The other thing is seed bank. So you can have suddenly a lot of rain, but if you don't have a very good seed bank with species different from the ones you already have, you also cannot change suddenly. So both things were very interesting. So this is very interesting. So those patterns were more related to long-term precipitation rather than short-term precipitation, which is interesting. So we have a very historical effect. And the most interesting variables were, for example, the end of the season was really dependent on the precipitation. So starting of the season, it doesn't depend very much on the precipitation. Most probably it's dependent on the temperature. Someone is studying temperature, you were studying the temperature. So everyone is studying temperature, but this is in temperate climates. Here, also precipitation is important, not only temperature. And then, in fact, it's important for ending the season. So if suddenly becomes lower precipitation, the season ends and everything became very yellow. And people from Greece here probably know that yellow starts maybe in April, maybe in May, maybe in June some years, right? So it depends really on the precipitation of the year. And this can change a lot productivity, because this implies 1 more month of productivity. In our countries is a lot. And that depends on the precipitation. So season length and season end depends a lot on precipitation, as well as the amount of evergreen vegetation, which was really good, interesting for that. So we had this kind of correlation. And some of the correlation, like season end, was linear. So more precipitation, more duration of the season end, or season length, up till a certain level. So this curve was not as linear as the other one. And for example, for productivity, so all ecosystem productivity, all that value, or just perennial vegetation. And it's very interesting that we get here a kind of point where even with more precipitation, we don't get more productivity. So from here to here, we are really limited on water. But here, no, it's management, soil, fire, land use, whatever you can find, all the factors. But here, it's limited by water, okay? Although with a lot of variability. So other things might change. In fact, we get this correlation not only at the landscape level, but when we relate tree cover and in VI. So we had a student that designed all the canopies of the trees. And we could validate this in the same gradient, but of course with lower data, for NDVI with tree canopy designs. Okay, so that was, we still have a lot of variability to work with, so we must know how much management can influence that, how much is the past history of the soil, how much is, fire, other things that can happen there, orography, but it's interesting that we still have a pattern for precipitation, okay? Just very quickly, I will run, we have been using LiDAR, okay, in a different area, in exclusion, so we have montado implies having some cattle grazing, normally cows at the moment. Before there were pigs, but now cows. So we had the treatments, 5 years exclusion, 9 years exclusion, 5 years exclusion, 15 years of exclusion, and control plots, okay? So we just use LiDAR. This is the special place where we've been using. We just use a portable LiDAR. LiDAR is like, do you know what LiDAR is? It's a laser that we can use. In this case, you use to the top and then to the bottom. And it just makes all the three-dimensional structure of the vegetation, okay? You can have a three-dimensional structure of the vegetation because it touches a leaf and goes down, so you know exactly where is the leaf, and then it goes with thousands of dots, and then you have like a cloud of dots, and then you can make a three-dimensional, I don't have a three-dimensional image of that, but we can do it if you want. So what she's done was like walking like that all the time, twice, to the top and to the bottom. So we've made all these white pathways, and the person from vegetation, Melanie, which also will be here tomorrow, was doing this only, okay? So superimposing some of the samplings in the same area and measuring shrubs. So this is the example of the landscape, 98, so exclusion, 15 years, 9 years, and then 5 years, and then control, okay? Then those are some of the species we've got, okay? And this is some of the plots we've got with LiDAR. So this is controlled, there were two types of control, one intensively grazed and one more not so intensively grazed, and then 5 years, 9 years, and 15 years, and you can see the shrubs growing here. As you can see, they were closing this. This is, so if you just look, this is 5 millimeters, 15, 25. So what happens is the layer of herbs, okay, and some shrubs, and canopy, yes. Whereas here you have a lot of shrubs, also because it's more low, so more shrub encroachment here. So you have more shrub encroachment in this area. And then here it's 5 years of exclusion. You start to have, you know, you don't have this like that. So you start to have a lot of shrubs and more, and then you close completely the thing. So you can also take a lot of metrics. So what a postdoc student I have made was calculating a kind of Shannon index, what all of you know. So she calculated the Shannon index based on this. So imagine that this is like a species. So she calculated the frequency and the number of species for each of these things. And we related with the biodiversity of shrubs. So this is the biodiversity of shrubs measured by in a traditional way. And this is the evenness and Shannon's index for LiDAR measured in that way. And this is the correlation between the two, which means that LiDAR, the structure, is really correlated with shrub diversity in that area. And we can use the structure as a surrogate of diversity. And in fact, LiDAR can be very useful whenever you don't have time to do everything, if you study very well the system, of course. Okay? So this is an interesting thing. Also because radar, which is satellite images, can also do that in large areas, okay? So, how many minutes? No minutes. Okay, I will not tell this story. The next one will be very short, but it's I don't have time. Just well, then this is really was an extra story. If I had time, don't worry. You can have the slides and you have a paper, so you can just read it, and there's no problem. Just wanted to, of course, have some time just to say that. So it looks like functional diversity seems to be a good candidate for early warning since it responds to changes in climate and desertification gradients. We can identify tipping points in space because we have nonlinear responses in space, both for productivity using satellite images and both for diversity and both for lichens. So we can have early warning indicators based on functional diversity. We can contribute with this type of work for the 3 United Nations conventions, desertification, climate change, and biodiversity. And of course, we are willing to test this hypothesis in other countries. So you are willing, if you are willing to also do something similar, please, we can work together and do something more relevant for the world. And just finish with, this was in Caatinga, which I will study now. I have a PhD student starting the work that Elise made in Portugal with functional diversity in Caatinga, which is the driest biome in Brazil. It's very badly known, but it has thousands of diversity. It's really incredible, and you can see this in the rock. This is not a garden, this is really nature. And it's really incredible, and it's so unknown, and it's the most different dryland I know. So if I test that, and if it works there, it will work everywhere. It's my idea. It's my hopeful, wishful thinking. So I would like to thank you all and ask for questions.